Thanks for coming to this talk. This one, it's cryptographic. I think this was the privacy track, but I've also mixed in some scalability stuff as well. It's a bit crypto heavy. I mean, somewhat maths heavy. So I'll try to go slowly through those examples. And if you start to zone out, just really listen to the points where I say just listen to this point, because there's only a few important bits that you have to lock on to actually get the most out of this, really. But yeah, so that's the topic, and basically I'll walk through a very simple example of doing a ring signature contract on Ethereum for voting, and show why, even though there's a bit of a trade-off between if you want it to be truly 100% private, it's quite hard to make it scalable. If you wanted to make it 100% scalable, then you kind of lose some privacy. So I'll show a few different approaches, and then come up with like kind of a hybrid model where you can kind of get the best of both worlds. Anyway, and by the way, if you want to know the about me, I always forget about this part. It's so I'm Matthew Di Ferrante. I do some security and cryptography at the Ethereum Foundation. Help on some of the protocol stuff, and besides that, I also run my own firm, ZK Labs, which you can see the site and the domain, the email domain there, which is a smart contract auditing firm, and also I do some crypto development there as well. Cool. So, all right, the overview. We'll go through the motivation. You know what sort of brought me to this talk. What brings me to this kind of research in general. A big part of this topic is going to be an elliptic curve refresher and a slight overview of bilinear pairings, because without that it doesn't make, I mean, the rest of the talk would mostly be just statements. So, and then we go through a naive on-chain voting scheme, say, if we're ever going to do e-voting on the blockchain, or those other blockchains that like to do on-chain governments, or whatever, like projects like Aragon, who have company governance on the blockchain. They all kind of need this on-chain voting, these on-chain voting schemes, and so I'll go through like an attempt to make those voting schemes somewhat private, such that if I vote for an outcome, you don't know that I voted for the outcome, but you know that someone eligible to vote voted, right? And I'll show, I'll show the bottlenecks we run into that, and then I'll go into a very high-level overview. Well, I mean, it's high-level and low at the same time, but we'll go through it on how to make that a bit more scalable. So, some of the motivations for the talk and this research in general is Ethereum is great for trustless applications, but if you do things naively, saying like if you just write a normal smart contract, if you're not really aware of the cryptographic primitives at offer, the privacy is not great. I mean, pretty much non-existent, and the gas cost is astronomical. If you were thinking about, like, if you ever wanted to do a blockchain, like a statal voting on the blockchain, like for an election, right? Those are usually millions of people. If you can imagine that normal elliptic curve signatures are 64 bytes per signature, you multiply that by the amount of, at the very least, right, without even including the message. If you multiply that by 64 million for just 1 million, an election with 1 million people, that's 64 megabytes on the blockchain for each election, and that doesn't really scale well, especially because that's the absolute lowest point if you're not even telling people what you're signing for. It's actually probably 10 times that, so it's like gigabytes per election, and it wouldn't really work out. So we can go through a scheme, and leveraging some crypto primitives, we can alleviate some of the problems of privacy and scalability. And also, obviously, mostly, I guess most elections, most sensitive voting protocols don't want to reveal the voters' preferences, right? So that as well, you don't want to do it absolutely naively, because even though that might be easy to program, it's definitely not desirable. working? Okay, great. Yeah, cool. Works now. So, hope you can see that a bit. It's cut off on the left there, but so I'll go through the elliptic curve primer because it's some of the stuff is necessary to understand the stuff later on. But elliptic curves have some special properties that are useful for zero-knowledge crypto systems. And if you're not aware of elliptic curves, I mean, I guess most people at a blockchain conference should be aware of them by now. But if you only know of them by name, basically, elliptic curves are the modern version of RSA, right? They are a public key crypto system, which has, it's asymmetric, where the key to encrypt is not the same as the key to decrypt, and so vice versa. So when you make an Ethereum address and you sign a transaction, that's done through elliptic curves. Bitcoin, Ethereum, and most of the cryptocurrencies use elliptic curves. Most of them use this one specific curve, which is SecP256K1, Bitcoin's original curve, and it's also kind of one of the things that made blockchains possible in the first place. I mean, besides the public key crypto system stuff, if you wanted to use RSA for the blockchain for private public key signatures, it would be ridiculous. The key sizes for RSA for the same level of security are something like 20 to 40 times larger, right? So we already have scaling problems with the quite efficient EC schemes that we have now. RSA would probably have made this unworkable, other than much, much slower. So anyways, the history aside, the elliptic curves have these properties which mean we can perform additions and multiplications on the public key without it's destroying its relation to the private key, right? So remember that public and private keys are really just two numbers. I mean, the private key is a number, the public key is two numbers. It's a coordinate point, but you can create a morphism that maintains the group structure, and that's kind of what gives rise to all these nice zero-knowledge proofs. The extension of that with bilinear pairings, it gives rise to ZK snarks, and there's so on and so forth. That you can do some cool stuff. I'll just read this out. The EC security crash course. The security in RSA is based on hardness of factoring large numbers, but the security in elliptic curves is based on the discrete logarithm problem. And so, what is the discrete logarithm problem? It means, so given y, that is the result of a computation, g to the x, right? So if g is, for example, 2 and x is 4, that 2 to the 4th power would be 16, right? And so given 16, you say, okay, what to the power of x base 2, taking 2, what is the exponent that gives me 16, right? And so on normal, on the normal real number line, that's quite easy because exponents have an inverse. But on modular fields, which is in RSA and elliptic curves and fields, discrete fields in general, the definition of discrete fields, you can't inverse this because there is just not an inversion, one-to-one inversion operation, right? So both in RSA and elliptic curves, we deal with integers on modular groups, and meaning the operations wrap around like in a clock, right? So clock arithmetic is modular arithmetic. If it's 2 p.m. and I say let's meet in 12 hours, we're not going to meet at 26 p.m. at 26 whatever. We're meeting at 2 a.m. I guess. Yeah, and this is basically what's being illustrated there in that simple calculation. But in cryptography, these numbers are obviously gigantic. They usually deal with numbers on the order of 2 to the 256 or larger, which is much bigger than what your clock can keep track of. But here's an example in terms of real numbers. It's much smaller though. So private keys are scalars, integers from the underlying field, and here's I guess it's not super. It's not a point that you'll come across as a non-cryptographer, but it'll make things a little easier to understand in the later slides. The elliptic curves are a group that is created from an underlying field, right? So it's kind of like the the curve or the group that substantiates the curve is really an emergent property of the underlying finite field. And so from one field, you can actually create many different elliptic curves depending on how you construct a curve, right? And as I said before, elliptic curves are crypto is much more efficient than RSA. A 256-bit elliptic curve key gives you 3072-bit RSA key security. And here's the fun tidbit on the homomorphism or the commutative properties. If you have a private key x and a public key GDDX, then the private key of the public key times a constant k to the power of x is x times k. I mean, I know that's a bit hard to follow just in spoken word, but this little trick is often used for vanity generation, a vanity address generation. Like if I want an Ethereum address that starts with 1, 2, 3, 4, 5, 6, 7, 8, 9, and I don't want to do the computation myself, but at the same time, if I let somebody else do that computation for me, naively, again, then they'll know my private key, right? And I definitely don't want that. So what I can do is I can take a x, right? This is mine and remains always secret, and I create the GDDX. And then which is pub, right? And I give the public key, GDDX, to an external party, and I say, compute an address that has GDDX as its component with 1, 2, 3, 4, 5, 6, 7, 8, 9 at the beginning. And so he'll find this third party. They will find a constant k that this should be y a bit more. Let's say k to the y, because if it's a third party, it's a different one. But they will find a constant k to the y that hashes to address 1, 2, 3, 4, 5, whatever, and they won't be able to use it because they don't have the primary component g to the x. But if they give it to me, then I can combine k to the x and g to the x together and create my vanity address. So it's kind of it's a nice way to outsource this specific type of computation. So let's go through a concrete example of elliptic curves in the application, which is this is probably the simplest signature scheme with elliptic curves, and it's not the one that's most used because this specific way to do it was patented. The patent only expired recently. Maybe I think now it's been maybe like a year or two. But we almost always use ECDSA. Ethereum uses ECDSA, and so there's Bitcoin and so on. But this one's much easier. And now that the patent is expired, you can actually use this. So the Schnorr signature provides zero-knowledge proof of knowledge of the exponent. So it's a mouthful, but that's the sort of very precise definition. The private key is an exponent, right? As we said, as we went over before in the elliptic curve primer, and the Schnorr signature is a zero-knowledge proof that I know the exponent without giving you the exponent, because obviously then I'm giving you over the secret, and this breaks the public key thing. So this means that a Schnorr signature reveals nothing at all about the private key. It does not provide any attacker any information for brute force besides what they would be able to do with just a full state space search. Okay. And here's sort of a protocol example. This is the interactive version of Schnorr. The non-interactive version of Schnorr just has like a hash in here somewhere, but the interactive version is just a bit easier to follow in your head. So I'm Bob, the prover. I want to prove to a third party that I have the private key X, and Alice is the verifier, again some third party, the public, whatever. And I create a witness value, W, and I take the G, the G in, this is standard notation of the curves. G is basically just the base, the group generator. It's a number that's like hard-coded in all software. So we all know G is public by default. So I take a G and I take it to the power of W, and I get a big W. So I send, and that's the blinder value, and I send Alice the larger W. And Alice already has my public key, right? So GDDX is my public key, and that's also public information. So she got it from a mailing list or something. So Alex, because this is the interactive version of Schnorr, Alex picks a random number, C is just a random integer, and sends me that integer. And then so to prove that I really do have X and I'm not just generating fake proofs, I take the primer for the blinded value, so the generator for the witness, and I subtract C, the challenge, times X, modulo the field, the field modulus, and I get the response R. And then Alice quickly verifies this is a proper signature scheme. It's secure as elliptic curve as anything else you're using elliptic curves. Alice can check that g to the power of R times g to the the public key to the power of C is the large value W. And what is that? Why does that work? This is here's a algebraic proof. It's a bit easier to follow, perhaps line by line. So you can say, if you remember one thing to keep in mind when you're reading this stuff is elliptic curves can really just be abstracted away as algebraic fields or algebraic groups, which means the laws of exponentiation, multiplication, addition apply just as they applied in elementary mathematics, right? So if you expand this stuff, you can say, look, g to the R times public key to the power of C equals W. If you substitute the terms, you get g to the W minus xc times g to the xc equals g to the W, right? And if because of the law of exponents, these two, the xc here and the xc here cancels out, and you're basically just left with g to the W, right? And so that's why the signature works. If only this specific one works only if you follow this protocol in order, right? Because if you're spend a bit thinking about this, if I'm not forced to pick the small w before I get the challenge C, then I can just pick any random w to make this work, right? Because these two cancel out. So if you plug in pretty much any combination of numbers here, it'll work as if you're not forced to do the commit beforehand. And again, this is the non-interactive version, which is more what people are used to in terms of signatures. When I create a signature, I can just publish it to the world without having to be involved in every verification. You just use the hash to force WC causality, because you cannot get C, the result of the hash, before knowing W, right? Because that's kind of the security that we all assume from hashes, right? So I mean this is the simplest possible version of replicators. So we can move on now. So on bilinear pairings. So the bilinear pairings is perhaps you've read about them or seen them mentioned just by name, but we got on the Ethereum virtual machine, we put in support in opcodes for bilinear pairing checks and operations late last year, and they allow for some interesting extensions to elliptic curves, right? And the extension being that normal elliptic curves, if you have two elliptic curve points, you can only add the elliptic curve points together, but you can't multiply them. You can take a scalar, an integer, and raise it to an exponent. You can take a point and raise it to an exponent that is a scalar, but you can multiply obviously two scalars together, or you can multiply a point by a scalar, but you can't multiply a point by a point. And this kind of extends that group to make it fully complete Gaussian multiplication as well. So as I said, it allows one extra operations, the multiplication of elliptic curve points. It's not normally possible on non-pairing curves, and the reason it's not possible is that if you did it on the same group, then it breaks the discrete logarithm problem. Well, it breaks the discrete Diffie-Hellman problem, which is decisional Diffie-Hellman problem, which is kind of like why signatures work. But if you do it in a very specific way, it allows you to do ZK snarks without breaking normal signatures. So here's an example of BLS signature. So given a private key x, message m, a hash function h, the signature is, the sigma is the message run through the hash function, which is a number, right? Remember, like, always there's numbers. Or actually, sorry, this is hash to elliptic curve point. So you hash to a number, convert that to elliptic curve point, and then you raise that to the x, which is your private key, and you get a signature, right? And the verification of the signature is simply you take this is kind of a way to encode bilinear pairings points, because kind of maybe how you can tell from the word bilinear, linear two lines, they are, a bilinear curve is kind of a pairing of two curves, right? It's a grouping, a combination of two curves. So you take the bilinear point, you have a point from the group 1, another point from the group 2, and you can do this special operation that allows you to shuffle exponents outside from inside these little parentheses to the outside. So if we remember that the signature here is just h to the mx, and as I sort of show here, I can take the h to the mx, and instead of keeping the x inside, I can take it outside of the parentheses, right? I can't move the x from here to here, but I can take it from the h to the m to the g, but I can take it outside. And again, since this is basically the same, but the x is just on the other term, I can move it outside the parentheses and check for equivalence. And this is kind of the very, very basic first step of why ZK snarks works and a whole bunch of other stuff. But the short, without getting into the math of why this works, pairings curves allow you to shuffle around the exponents to check for equivalences, something that could not be done on normal elliptic curves, because if you could do this on a normal elliptic curve, then you could take the x out into a base that you know like a factor of, and get the bar key for it. Cool. So here's I'll go through an example of normal ring signatures on normal elliptic curves, and then I'll show how they differ on bilinear pairings. Well, the properties of this signature. Some nice benefits, some not so nice, and then I'll go through a version on that uses the properties of bilinear pairings. But anyways, so elliptic curve example, ring signatures. What are they exactly? So the concept was first introduced in a paper titled "How to Leak a Secret" by some of the RSA authors. It concerns using keys in a group instead of using them individually. To prove you have a private key from the group as opposed to proving ownership of a specific key, right? If I sign normally from an Ethereum address, I'm saying, Ethereum address 123 blah blah blah, it's mine, or whoever signed it at that moment has ownership of it, and here's a proof to the signature, and this allows me to transact or whatever. This one is if I have a set of public keys or a larger group, I can prove that I am from the group, but not prove exactly which key I correspond to. Kind of like why they were introduced in the first place, they're useful for whistleblowing. If each public key, for example, belongs to a government official, the official can leak some classified data proving that they are indeed a government official without outing themselves as individually as the whistleblower. If you're in a government party of 100 people and we're in some advanced government that has learned how to use computers, and they understand cryptography finally. You can say it's something dodgy is going on in some lobbying or corruption. You can say, hey, look, here's a signature from one of the parties that would be privy to this, but without immediately getting themselves assassinated, right? Because they now they know exactly who leaked it. But it's just somebody from within politics, right? That would be a nice thing. So again, the ring signatures are just one type of zero-knowledge proof. They prove X and only X. Zero-knowledge proofs allow you to prove knowledge of a secret without revealing anything about the secret. So the next analogy I have for this class of properties is, say if I choose a card from a deck of cards, and I want to prove to you that it's a red card, if I just show you the card, it reveals more than the color. It reveals the suit, the number, and so on, everything. And I don't want to reveal everything. I just want to reveal that one bit of information, which is the color. But if, on the other hand, I just take my card aside from the deck, and you assume that this is a deck with 24 black cards and 24 red cards, and I haven't messed with the deck. And if I take all the black cards if I take all of the black cards out of the deck and I flip them up, and there's no more black cards in the deck, I prove that this card I set aside in red, right? Perhaps you unpacked the deck, and so you know that I haven't thrown any random cards in. So specifically, the zero-knowledge proof in Rigorous signatures is called a zero-knowledge proof of set membership. So let's take this primitive and try to do something useful, practical with it. And so we can create private voting rounds with linkable ring signatures by requiring each user submit their public key to the contract, a public key that they want to be. In this case, you would probably have a setup step. If anybody is aware of, for example, the Estonian government, they give out, I have one of the Estonian EID, e-residency things, and the Estonian residency card has a chip in it, a smart chip, and that smart chip can be plugged into a smart card reader, and if you mess with the pin, the software, you can create signatures from it, and the signatures can derive a public key, which then you can go check against the embassy's website or some server they run that says, look, yes, I have a certificate where I signed for this public key, right? So all public keys, that all signatures from this public key are very likely from me, Matt Di Ferrante, because the only way to get that card with the key in it, and you can't extract the key, well, assuming that the smart card is safe, the only way to get that card is to be me and go to the embassy and show my passport at the embassy, right? And if I lose the card, you still can't sign as me because you need the PIN, and again, you can't reset the PIN unless you're me. So, for example, the public key submitted to the contract could be something from one of these e-identities that Switzerland and Estonia now have, government issued, or some one-time thing where you know that you're not going to get Sybil attacked. And so say that there's a group of 100 people that need to sign, and we deploy the smart contract saying, wait until you get 100 public keys that commit to signing, and great. And now once they have all joined, each user is entitled to one and only one private vote, right? And through some extension to rig signatures, we can make sure that even though when I sign, you don't know that I, Matt, have signed, you know that if I sign 2 times, you can detect that I tried to double sign, but you just don't know who. So you can prune all double votes. The smart contract can do it automatically, but you still don't know who signed, but it must have been one of the people from the set of committed public keys. So here's a little visual representation of that. So you can see if we were using this for example, anonymous, the ring signature can be used for anonymous payments or voting or whatever. You can see that the green, if we imagine identities here as keys, the green key, the yellow key, and the red key, these are still the same colors. I think but yeah, they are still the same on this side, right? Except for the way that the signature is constructed, the signature contains a component from each key. So if this person commits some funds and a key, this person commits some funds and a key, and so on, then only the person who has the private key can then withdraw from this, right? As again, for example, a ring mixer. And the signature, it reveals no information besides the fact that it's a signature from this group, right? So you know that if I put money in, no one can steal my money, but at the same time, when I withdraw the money, no one can know that no one can know that the first withdrawer was me or that the last withdrawer was me, right? So it makes sense. I think that's not too difficult. It's just some crypto magic, but take it as truth. So there's a problem here. If you wanted to use this for just if you wanted to use naively, again, for larger scale stuff, through normal ring signatures, we have indistinguishability between participants. I can't tell the first and the last signer apart. I don't know who they are. But there's an obvious scaling problem. So a vote from 1,000 people will require 1,000 individual signatures that are 1,000 sig size bytes each. And for this specific implementation, at least the one that I did myself, it's large. It's quite large. It's like more than 100 bytes per signature, per individual signature component. So again, this would be 1,000 times 100 times 1,000, which is ridiculous. It's a ridiculous size. And I think even if you do it with the best opcodes right now, the most optimized EVM assembly, you hit a limit about at a ring of 10 people, 10 to 15 people. So if you want to do a mixed type network like you have in Monero or in Zcash, where the cloud of anonymous users is very large, that's just not possible. At least not if you program it this way. But there's some hope if you use instead bilinear pairings. And so I'm gonna get ready for the next slide because I didn't really have time to make the pictures pretty, so there's just a bunch of math on there. Consider a simple setting in which several signers all wish to sign the same message M, right? So for example, if somebody makes a proposal on the mainnet saying, where we want to upgrade the smart contract, it's a token contract, and the token holders are eligible to vote on whether it can be upgraded or not. And if they sign, then great. If they don't sign, then it's just taken as an implicit no. And the message, again, would be just be to upgrade. And so imagine that we have a threshold aggregate n of n. So this is a simple aggregate n of n, meaning that it's not a it's just an aggregate n of n, not a threshold m of n. So say that there's 1,000 users and I want 700 to say yes, right? If we don't get that 700 number, nothing happens. So again, consider that the message is the same, just a smart contract hash, for example. The signers, the signer I, their secret key is x to the xi, and the public key is y sub I, whatever. That's g to the x sub I. And then the signature is created a bit differently than we were doing it in the Schnorr example. So the signature here for each signer is the one that we went over here, right, from BLS. So we take our public key, we take our private key, the exponent x, and we raise the hash curve point to the power of that, right? So our signature is the BLS signature, so it's not the Schnorr signature. And remember these properties where I can shuffle the exponents out of the curve, out of the parentheses, to do simple computation shortcuts and check equivalences. Right, so now we know that each individual signer's signature is created by hm over x. This, if you don't have the mathematical background, it's just this it's product sign, meaning that the aggregate signature is simply all of the individual signatures from each participant multiplied together, right? Remember, we couldn't do this. If I take a signature on the mainnet for some Ethereum transaction and another signature from the mainnet, I can't multiply those together. You just can't do that on normal elliptic curves. But because we're on a bilinear pairing curve, we can do that. So the final signature, the n of n signature, is simply the signature from each participant multiplied together. So yeah, in other words, you have each individual signature is just h of m summation to the individual's private key. So the aggregated signature is just basically what we did over there. And for verifying the smart contract, we only need to we can accept if and only if the elliptic curve, the bilinear check G over the aggregate signature is equal to the product of all individual signatures, for each individual public key over the message, right? And I know it's a bit hard to visualize this without having a few more pages of math, but basically this just says it's basically saying the same thing as this here, right? We take each individual signature and multiply it. So we have, say that we had 10 signers, we would say sigma 0 times sigma 1 times sigma 2 times sigma 3 and so on, and that's sigma complete, right, or sigma whatever total, which is the aggregate. And so this one would be, we take the elliptic curve point, the pairings point y0, which I mean, remember, it's just g to the x0 because that's what this is, right? Over hm, and then we multiply that by e y1 and so on, and ey2, and that, because of the properties of bilinear bearings, we can make sure that it is the same as that without anybody losing any of the without anybody losing their private keys, right? But there is one thing if anybody managed to follow the rambling, is that you lose the privacy here, right? Because for each, if you're sort of looking at the, if you're paying attention to the definition, each signature is self-sufficient. So you can test each signature independently, even if you don't have the n of n, right? And I can tell that public key 1 voted for this message, and I can tell public key 2 never voted, so they didn't want it to upgrade. So what we can do instead is we can, if we wanted to have the best of both worlds, again, for the nice indistinguishability from the normal elliptic curve and the scalability to be able to do the check on chain without spending $1 million, you can do this process. You can do this process first off chain and get the result, with because you can do. You can say like that bilinear pairings are backwards compatible, right? So you can use bilinear pairing curves for normal elliptic curve stuff, but you can't use elliptic curve groups for bilinear pairing, non-bilinear pairing groups for bilinear pairing stuff, right? So you can use one part of the key to do this process and get the initial sort of vote distribution, and then a third party can come in with the a third party or a multi-party process or whatever can come in with the through this process and create an aggregate key. I mean, there's a bit of another version of this one, which is threshold signature, is a bit more efficient, but requires more previous setups, and then there's I'll go on the next slide, I think. So with all that, assuming the public keys have already been registered on chain for other purposes, we reduce the voting step data cost from 1,000 times 1,000 times the size of the signature to really just the size of the signature, because again, we have to assume that the public keys have to be on chain anyway, because like otherwise the participants must register to vote at one point or another. There are ways to limit the amount of stuff you put on chain, but you're kind of always limited by the initial step. But if you assume that eventually we all have EIDs that can interact with the blockchain or something of the sort, then once you put your ID on the blockchain for one purpose, then any smart contract can refer to it, right? So it's like a one-time storage cost and just many-time reads cost. So, and there's other extensions here that have further setup steps where it's possible to reduce this even further, such that any M of n creates the same signature, a threshold signature. So, for example, if you have like a 7 of 10 threshold signature, any 7 keys in the in the set of 10 keys, signing will create the exact same signature output, right? So whether it's the first 7 or the last 7, different keys, different key sets, they'll still create the same signature. And this is, yeah, again, through cancellation in bilinear pairings, which is only possible in bilinear pairings. And the threshold signature is used by one of the other projects that I think is presenting here this week, Definity. They use it in their consensus algorithm. And for even more setup costs, initial setup costs, and a bit more exotic math, you can create a constant size proof, or basically really like you can kind of see it as a smart hash that can hold verifications for practically unlimited amount of events, which is called a set accumulator. Set accumulator is, again, is basically like just kind of like a hash can hold a fingerprint for an arbitrarily large size file. A set accumulator index can hold, can be a verification for like an arbitrarily large amount of events. Arbitrarily large amounts of events. You know, there's always a limit, which is like log n to verification time, but that's a more computation theory thing. Cool. And yeah, so that's it was a bit of a foray into sort of some of the trade-offs and how you would go about constructing the stuff. And you know, even if you think that Ethereum is not scalable now, blockchains are not scalable now. A lot of people whine about this. You know, especially in the media. You know, the further away you get from the understanding, the more alarming the articles get. But you know, it's not. It's like it's just because you know it's a pretty nascent industry. Cryptography itself is not liked by many people. I mean, sure, it's fancy. Everybody likes to talk about the magic, but very few people like to write cryptography code. So you know, this progresses slowly, but it doesn't mean that it's impossible, right? Again, it's just you know, we've only been around for a few years. Cool. So, any questions?
Yes, just revisiting that. Should I get a mic or maybe everyone can hear me? Yeah. So just about the threshold BLS thing.
Yep.
About the threshold signature, just that if it's Lagrange interpolation based, like aren't most threshold signature schemes based around a Lagrange interpolation? So you would get this property that the same sets or different sets of signature shares lead to the same underlying signature on the same value, or is it just that like there's no random witness data in the or random commitment data in the signature?
Well, I mean, surely if you have random commitment data, you probably come up with different outputs. Yeah, you're right that most threshold signatures are based on Lagrange interpolation or similar things where they come up with the same. I mean, the one that I showed is the aggregate signature, right, which is not threshold, and so obviously you have different, well, I mean, there's only one output anyway, right, but it's just, there's not an event. I think that there may be ones that are based not on Lagrange interpolation, but it's, you know, I wouldn't be able to name it to you. It's fuzzy stuff that I've just gone through in the research. But yeah, I mean, like the vast majority are just based on, yeah, what you said.
So just why is the pairing necessary then for this uniqueness property? I mean, if the Lagrange interpolation is enough to give you the unique signature on the same value, regardless of the key sets used.
I mean, it's, well, like it doesn't work on, I think, yeah, there's like I guess it depends on what you're exactly trying to use it for, and you know, the way that you are setting up the group. I mean, for like key share setups, I think you do need bilinear pairings. But you know, for example, yeah, like you're right that you can do ECDSA in a key share way with Lagrange interpolation as well. I think it just kind of depends on whether you're using it as just like that one standalone event where once it comes together, you know, you need to have that interaction process every time it comes together, or whether you want that first DKG setup and then from then on you want the non-interactiveness, right? So yeah, it depends on the use case.
All right, thanks.
Cool. Any other questions? Yep. Give that Stefan to all over there in the back.
Thank you. I have a few questions, in fact. So my first question is about the ring signature. When you were talking about the voting process, well, it solves a sort of problem that you don't really reveal the identity of the person. But what about Sybil attacks? How can we solve such a problem and make sure that people do not generate multiple public keys to have multiple identities to be able to vote? So
Yeah,
that's
I mean,
first
so
question.
I feel I went over that briefly before. Basically, again, if it's like a governmental election, for example, right, you can only use the key to sign that the government has signed off on, right? And like in the payments example, right, to make sure that somebody doesn't withdraw more than they put in as well. I mean, nothing prevents them from being more than one participant, but every time they try to be more than one, it costs them more money, right? So there's economic incentives, there are permission incentives. Yeah, the Sybil problem is a problem in environments where there's no economic penalty for trying to be multiple people, but it's not, I mean, the Sybil problem is not really a cryptography problem. Again, it's an economic incentive problem. So the solution there depends on the use case, right?
So like using security check or some security deposit or something.
Yeah, or again, or like having some sort of in-person verification step before you're allowed to, sign.
Okay, and my second question is about scalability issues, and when you use, for example, secret sharing protocols, and you do any sort of multiplication or whatever you want off-chain to solve scalability issues, and then verification, you do it on-chain. So for example, like I was thinking of the other day of how to do, for example, Shamir secret sharing verification on-chain, and then you have to do interpolation function. Would we use a smart contract for that, or how we do that like on-chain?
I mean, it's a very broad question. It very much depends on the use case. Some use cases are okay with, or more accepting of like massive off-chain computation and on-chain checkpoints, right? If you can use something like that, then true bit scheme type stuff works well. Maybe we can use where something like Plasma, similarly, right? It's a lot of off-chain, side-chain stuff, and then eventual settlement. If somebody tries to settle a wrong stake, then somebody can create a conflicting proof. I mean, it's the solutions there vary massively depending on what you're trying to do. It's always a equation between how much overhead you want, right? Because an off-chain network takes overhead versus how much of it do you want to be non-interactive and just immediately on-chain.
Thank you.
Hey, thanks. Really interesting, Matthew, as usual. Quick sort of pragmatic question. When do you think we can see the first implementation of these signatures types in Ethereum or other blockchains, and if so, which one? Do you have a rough idea in terms of timelines?
So the Nave one, sorry, not the ring signature private key one. If you look on my GitHub, I mean it's not on here, but just Google my name. It's like one of the first links. I already have an implementation of that. But I guess I said it's ridiculous. It's just way too inefficient. I mean, even with the bilinear pairings opcodes, it's still not something that, I mean, if people actually started using that as a main service, the chain would go down again, right? Well, not go down, but I mean, it would be gas price would go high, it would be very high. The other one, for the BLS compactification, probably the version would not have privacy, but again, for on-chain voting, like DAO type stuff, right? Soon, perhaps. I mean, it's not that complex. I'm sort of in talks. Me and Dean, who works in ZK Labs, we're going to talk to Aragon about it, and we have some stuff in the partnership. But soon, probably, hopefully, maybe like this month. I don't know.
All right, thank you very much.
Any other questions? No more questions then. Cool, thanks.